All right, so now we're doing worksheet number 4. This is going to be on resistance, Ohm's law, uh, and a few other things that we're going to focus on. A little bit of AC circuits. So once and AC circuits here. So, we have our electrical current equation, but we kind of focus on resistance on this worksheet here. So the question is, what is resistance? Well, that's just the electrical resistance of a circuit component or device is defined by the ratio of voltage applied to the electric current, which flows through it, right? So that's the ratio R equals the voltage divided by the current that flows through it. So that's where we get that equation, V equals IR, or R equals V over I, as I just described. And then the resistance of the wire can be, calculated using this equation. We've seen this a few times where that rho value here is that resistivity. We have the length and then the cross-sectional area. Ohm's law, this is something we should be pretty comfortable with. And then we have our equations for electric power at the bottom, number 5 here. And for describing an AC current, I think it's just important that we clearly delineate what the difference between AC and DC is. So DC, I'm going to say DC, right? I mean like either direct current or alternating current. What a DC current is that the current dash voltage remains constant over time. Okay. So that's kind of an important thing to recognize there. And alternatively, with the alternating current, the current and voltage alternates over time, right? So it's kind of something that is just good to remember. And we have those equations. It can either be I equals that I naught sine 2 pi frequency times t, or that can be replaced with the v there. But the important thing to note is whenever you write these equations where it's going to either be, I of t is equal to I naught, dot, 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 or v of t is equal to v naught. This value right here in either case is going to be the max values. Sometimes you see them write I naught, sometimes you see them write I max. It goes both ways. It's important to know that the value that's here, that's the max value. And I think that just kind of relates back to the homework that we've already completed here. And then to describe an AC current, we just need to establish what our equations are. So first is like these max and RMSs, like what is all that stuff? Kind of the important thing to remember here is if you're talking about voltage, you're talking about current, either case, whatever the max value is equal to root 2 times whatever the RMS value is. So we learned about VRMS and IRMS. So, if that was a V here, that'd be the VRMS, or it can be the I here, the current here. So just remember that kind of way we can work things through. And the next thing that's kind of important is, VRMS is equal to, this is, basically, this is Ohm's law, but we're writing in the RMSs just to be clear, like that. And then the final thing is this comment on the average power, right? So that power average is equal to P max over 2. So you know how to rearrange this equation and to solve for everything. And then basically everything else you need to ever solve for this P average value right here is this equation right here. So that's also going to be equal to, V RMS I RMS. That's going to be equal to R times I RMS squared, and also V RMS squared over R. Cool. Are there any questions on that? We're pretty good. Okay, so we kind of established our equations. This isn't anything too crazy. And we can just dive into question number 1 here. So here we're asked to calculate the ratio of the resistance of a 10 meter of an aluminum wire. We know the diameter, and then we also know that it's a ratio, right? So we know in comparison to the copper wire, and we're also given the diameter there. We're given both resistivity values, and we're just going to calculate the ratio of resistance. So for question number 1, here we go. What's the equation we're going to be using? It's going to be that equation number 2 up there. I like the subscript label, just kind of cleans it up. Okay. And what's the area? Well, that area is equal to, we have a diameter, so we're working with a circle. We can solve for the area as such. And then the same thing with the copper. Okay. Oops, sorry. No equal sign here. Like that. There we go. Actually, I'll do the copper 1 second. Now we can just plug in everything. So I'll do the units and everything on this first go, just to be very clear. Okay, and when you work all that out, what you're gonna get is the following. And then we do the same thing for the copper. And, you know, this is kind of old news at this point. And we're just about done here, but we're asked to solve for a ratio. Sorry about that. Clear my throat. We're asked to solve for a ratio. So we're going to do the ratio of the copper, or of the aluminum to the copper. Whenever we do a ratio, you know, the units cancel out. So the answer comes out to the following. Okay, so pretty simple equation, just solving using that resistance of a wire equation, which is this guy right here. And number two, again, kind of similar, but I just want to show what happens when we're working with a per unit length here. So we have a DC electric transmission line. We know the current, and we know the resistance per meter. And we know how far the student's hands are apart. So what is the potential difference between the student's hands? Well, we have to use our equation that solves for potential difference. So that's going to be V equals IR. And, you know, this one's just kind of quick plug and chug here, but the important thing is recognizing this per unit length. So whenever we're given a value that's in a per unit length form, that means, you know, it's going to be times or divided by some meters, but we also know how far apart the hands were, so we can cancel out these meters, and we just come out with an answer that's in voltage. Volts. Okay, so 1 and 2 kind of just working on the language of this kind of worksheet here. So in question 3 now, or let me just say this real quick. Any questions on the first two? I'll pause the recording real quick. Okay. So now we can move on to question number 3 here. And this is where it kind of becomes a little more complicated. So here we have a 12-volt battery, 2 resistors and 2 capacitors are connected as shown below. After the circuit has been connected for a long time, what is the charge on each capacitor? So this is an RC circuit. RC circuit means there's resistors and capacitors. That's it. So we know the voltage at the, here, maybe it'll be easier if I draw this actually. Here, I'm going to draw it nice. So give me 1 sec. I'll pause the recording so it's not painful. Okay, and we're back. So right off the bat, we can see that all these circuit systems are in parallel. The capacitors are in parallel with that resistor. So we know that the voltage at this resistor here is going to be the voltage at these guys here. So just to remember that, I'm just going to do a little, just this right here. That reminds me that they're all the same voltage. I don't know. Or you can just remember it if you have a good memory. I think I'm just writing it just so people aren't confused on that logical step there. So to be able to find what that voltage is, you need to first find the current. And the last thing I want to add is that a fully charged capacitor, when they say, you know, the system's been running for a long time, it's been connected to the battery for a long time, anything along those words, that tells you you're at steady state, meaning there's no current actually going through the side. They're fully charged, okay? So how do we work backwards for that voltage? Well, the first thing we need to do is look at our 2 resistors. Looking at our 2 resistors right here, we can see that we're just going to be adding, right? So the REQ is equal to 1.3. Okay. And that's going to be equal to 4.6. And now we have to find the I, so I'll call this like part 1 of this question. What we're going to find next is that IEQ value, which is equal to V over REQ. What's that V? Well, that's equal to 12, right? That's the whole system. REQ we just solved for is that 4.6. So this whole thing comes out to be 2.6 times 10 to the minus 3 amps. Okay. So using the explanation just provided, we can now solve for the voltage at that 3.3 kilo ohm resistor by just using Ohm's law. Plug in all the same values. You know, that's that 2.6 6 times 10 to the minus 3. What's the resistance? Well, you know, we're at the 3.3 kilo ohm resistor there. So this V is out to be 8.58 volts. Okay, so now all we have to do is use this value here to plug into each of the capacitors to find the charge. What's our way to find the charge? Well, that's just going to be our Q value, CV, and then Q, again, CV. Up here, we're going to be working with the 12 times 10 to the minus 6 capacitance times that 8.58. And this was at 48 times 10 to the minus 6 times 8.58. Okay. And the important thing with this question is just that stepwise approach, which led me to the answer here. So I'm trying this and I'll explain. So basically that the voltage here is the same as these guys right here. And that's because we can see how they're all in parallel with each other. And then the next thing that's important here is this: when it's fully charged capacitor, it's at steady state. So there's no current there. So that's why we have to use the current here to find the voltage drop that's here and then equate that voltage drop to each of these three. So just kind of equipping you with some knowledge type question. Let's see if there's any questions. Okay, continuing with question 4 here, we have this figure they provide us. We have 4 resistors, all of which are in series. We know what the total voltage of the battery is. That's that V max, right? So this is question number 4. We'll write this. We remember that's equal to V max, and then that's equal to 60 volts. And it's the sine wave doesn't matter. The first thing we want to do is find the RMS value of the current. So we went over a few different ways to solve for RMS of the current, but let's just, you know, plug in what we know, right? So the way we're going to be able to solve for the current value, that's that IRMS, we're going to have to use VRMS, which is equal to IRMS, and then the total resistance of the system. Well, they're all in series, so that means we can just add the sum, you know, it's the sum of all of them, right? So is equal to 30. Okay. And we have to find VRMS, but we don't really have anything about VRMS, but we do remember one of our other equation, which is V max equals VRMS root 2. So we should have to divide both sides by root 2. 60 divided by root 2 is going to be equal to 42.43 volts. At this point, we have enough to solve for that IRMS just by rearranging this equation. You'll see that we get an IRMS equals 1.41 amps. Okay, that's A. Looking at part B now, we want to determine the maximum voltage through the 10 ohm resistor. So we're going to have to, well, first is, you know, the current's going to be constant throughout the entire, the current is constant throughout the entire resistor, right? So when we're looking for, we're going to need to plug in a V max. It's that Imax, and then the resistance of the 10 ohm resistor. Okay. And what is that Imax equal to? Well, Imax is just equal to Vmax divided by Req. So therefore, that max value at the 10 ohm resistor is going to be equal to Vmax divided by Req. That's what Imax is, right? And then multiplied by that 10 ohms. Okay, so it's going to be 60 over 30 times 10 equals 20. Cool. And the last part here, part 3, is what is the average power of the entire system? So solving for average power, kind of a kind of a freebie here. We have many equations to choose from. What do we have? We know what the IRMS is, and we know what the total resistance is. So might as well use that. We can solve just with a simple plugin. Cool. All right. Let me pause and take any questions.
Wait, do you mind
All right. Now, question number 5 here is a little bit more involved. It might be kind of not something that I've seen it come up on other midterms, so I don't want to just exclude it, right? So this is basically a step up, step down transformer situation. And this is, when we see like power lines and like how they work. And basically what happens is the power leaving the power station goes through like a step up, and then it becomes a lot higher voltage, and that causes the amount of voltage that's just lost like in the wire due to like, every wire has some amount of resistance, right? That's that whole equation that's like this, So every wire has some amount of resistance. And when it's stepped up, that means the voltage going through it is stronger. The amount lost is actually less. So remember that. When it's stepped up, the amount lost is less. That'll kind of direct your answer in this, or let you kind of think, did I solve this right when you solve these types of questions? And I'll show you what I mean in a sec. So the power put into the wire will be slightly less than the output, and that's just due to that resistance. So in this question, we know the power station delivers that much power at 12,000 volts to a city that's 10 kilometers away through 2 copper wires. We're given the resistivity values, and we know the radius. What percent of power can be saved if we're using that step up, right? So it's delivered at 50,000 instead of at 12,000. So we're kind of asked a two-parter here, and we're going to need to do a percent like difference calculation at the end. First is we want to know how much power is delivered through the wires, and then how much is lost through the wires. And then we're going to do comparison of those two questions relative to each scenario. So, like I said, the first thing we're going to solve for is that power that's delivered. So PD, I'll just call it. PD is going to equal to I1 V1, okay? And V1, that's going to be that 12,000. But I1 we don't know yet, right? And we need to rearrange to solve for that. So for I1, it's going to be equal to PD, which we know, right? PD is that, what do they tell us? 750 kilowatts, right? Divided by V1. So now 750 times 10 to the third watts divided by that voltage they tell us it's currently acting at. So now we know the current in its current, the current in the present iteration, right? That it exists in. The next thing we want to solve for is P lost. So P lost, what's our equation we're going to use, is going to be that I1 squared times R, okay? But we don't know what the resistance value is, but we do know how to calculate it. So we'll say where R is equal to that rho L over A, right? But the key thing to remember is there's 2 wires. And that 2 wires is a little, those little words right there can really mess up your answer if you're not careful. You do the same calculation, except you need to multiply everything by 2 because there's 2 wires. So just be mindful of that. You plug in the resistivity, you multiply by how long it is. They said 5,000 kilometers. Yeah, so that's 5,000 meters. And then you're going to divide it by that area equation. So 5 times 10 to the minus 3 squared pi. Okay? That whole expression comes out to be 2.14 ohms. We can now calculate P lost, which is equal to the current in that iteration squared multiplied by the resistance. We just calculated for that. And now we can calculate how much is lost in that 12,000 volt scenario. That's equal to 8,356 watts lost in scenario, in the 12,000 volt scenario. Okay, so now we have to do kind of part 2 here. We're gonna have to recalculate basically the same thing, right? So the first thing we're gonna do is calculate the new P delivered, given the second iteration. So I'm gonna call it PD prime. And we know that that's equal to I2 V2. we have to rearrange to actually find that to find that I2, which is equal to PD prime divided by V2. Okay, plug in everything. Now this part's a little similar, but we're just going to be dividing by a greater voltage, right? That's equal to 15 amps. We can now calculate the P lost. You'll notice here that this time I can skip over calculating the resistance value because it's going to be the same resistance value from part one, right? So what's different is that I2, but same resistance, constant there. So now we just have to multiply that 15 squared times that 2.14, and we can come out with the new power lost, 481 watts lost. Now this is what I mean when I say that you kind of have, one second, let me finish this. And with the step up, right? So that means there's a greater voltage, there's a reduced loss, right? It's basically like launching it with more power, or however you want to think about it, right? So if this value right here came out to be bigger than this value, that means, uh-oh, I messed up somewhere. And, we say power in scenario 2, right? But by what percent, we have to, use that percent calculation from, I think this is like Gen Chem, we learned this, divided by P1 times 100. What's that? 8,356 minus 481 divided by 8,356 times 100. And the percent difference using the step up transformer is going to be 94% conserved. So it makes a huge difference. And that's why between, like the factory and our house, it goes to like those little things. They look like they have the little loops here. And then it goes to the big power lines, like in the new Spider-Man movie where he fights the electric guy. And they get really powerful right here, super strong. But then before they get back to our house, they get really dampened. So our house, doesn't like go crazy, right? So in this intermediate right here, there's a step up. And then before it gets to our house, there's a step down. But the greater the step up, the less is lost right here. And this doodle right here, that's an NFT for you guys to screenshot. All right, let's take questions.